A rational function has an equation of the form f of x equals a of x over b of x, where a of x and b of x are polynomial functions and b of x does not equal 0. In order to graph a rational function, it is helpful to locate the zeros in the asymptotes. A zero of a function of f of x equals a of x over b of x occurs for every value of x for which a of x equals 0. So you're going to see that these rational functions are very similar to the reciprocal functions of the last section. With those functions as well as these rational functions, we're looking for the asymptotes first. The way you find the vertical asymptote is the same as we did for reciprocal functions. The f of x has a vertical asymptote whenever b of x equals 0, and they're referring to b of x as the denominator. So you could say that it has a vertical asymptote wherever the denominator equals 0. They also have horizontal asymptotes, and horizontal asymptotes have a little more complicated to find. First off, that they will have at most one horizontal asymptote, and sometimes they may have 0. And the way you find horizontal asymptotes is you look at the degree of the polynomial. The degree meaning the highest exponent of the numerator and the highest exponent of the denominator. So they are also referring to a of x as being the numerator and b of x being the denominator. So if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is at the line y equals 0, otherwise known as the x-axis. And if the degree of the numerator equals the degree of the denominator, the horizontal asymptote is the line y equals, then we look at the leading coefficient of the numerator over the leading coefficient of the denominator. And below there are several different examples. First example is, notice that this one has no horizontal asymptote, and we could see that from the equation because the degree of the numerator is a 2 and the degree of the denominator is a 1. There is an x to the first power on that one. So since the numerator is higher than the denominator, there is no horizontal asymptote. However, there is a vertical asymptote located at x equals negative 1 because x equals negative 1 would set the denominator right there equal to 0. Here's one with one horizontal asymptote. Starting with the horizontal asymptote, we could see that the degree of the numerator, since there are no exponents, the degree of the numerator is 0, and the degree of the denominator is a 2. It's an x to the second power. So the numerator's degree is less than that of the denominator, so the horizontal asymptote is at f of x equals 0 or on the x-axis. This one has two vertical asymptotes because there are two values of x that would make that denominator equal to 0. If I were to set x squared minus 1 equal to 0, I could solve that by adding 1 to both sides and then square rooting. And when you square root inside of an equation, remember that you use plus or minus. So x equals plus or minus 1, so that's why there are two asymptotes, one located at x equals 1 and one located at x equals negative 1. And then the final example, this is an example of one vertical asymptote at x equals 3 because that's what would make the denominator equal to 0. And since the degree of both the numerator and the denominator are both 1, they both have exponents of 1, then the horizontal asymptote would be located by finding the leading coefficient of the numerator, which is 2, over the leading coefficient of the denominator, which is that hidden 1 there. So that would be 2 over 1, which is why it equals 2. So let's do some examples. First thing we're going to do is find any asymptotes, and then once we find the asymptotes, we will do a pretty extensive t-chart, trying to keep close to the vertical asymptote as possible, including adding some fractions in there in our t-chart so that we're very close to the asymptote to get an idea what is going on as we near the asymptote, whether it's increasing sharply or decreasing sharply. So graph f of x equals x cubed over x minus 1. So first off, finding the asymptotes. There is a vertical asymptote because when we set x minus 1 equal to 0, we get x equals 1, so that is the vertical asymptote. And there is no horizontal asymptote. And the reason there is no horizontal asymptote is because the degree of the numerator is 3, which is higher than the degree of the denominator, which is 1. So no horizontal asymptote, a vertical asymptote only. So I'll go ahead and I will draw in the vertical asymptote at x equals 1. So that's going to be right through here. And then we're going to do a t-chart. And in our t-chart, let's first start out by picking some numbers that are close to the vertical asymptote. So that would be on the right side, we could use 2, 3, and 4. And on the left side, we could use 0, 1, and 2. So to plug in those numbers into the original problem, we would have to plug in 2 to the third power. Change that color to blue there. 2 to the third power, and we'll keep that permanently, over 2 minus 1. And 2 to the third power is 8, and 2 minus 1 is 1, and 8 minus 1 is 8. So that would be the ordered pair 2, 8, which would be about right here. And then we do that for each one of the numbers. So for 3, we would have 3 to the third power over 3 minus 1. 3 to the third power is 27, and 3 minus 1 is 2. So 27 over 2 would be about 13.5, which is running off our graph pretty quickly. So 13.5 is probably about right here, I would say. And then when we do the rest of the t-chart, this is what we get. And there we are. So now I can see that I've already graphed 2, 8, and 3, 13.5. So then I would graph 4, 23.3, which goes way off the screen, so I'm not going to bother graphing that. And then on the other side, the asymptote is 0, 0, negative 1, 0.5, so over 1, up 0.5, and negative 2, 2.6. So we can see it is starting to get a little bit higher on that side there. If I wanted to see what else was going on the left side, I could use negative 3. And when I plug in negative 3, that would be negative 27 over negative 4, which is about positive 6.75. So you can see it is increasing to the left pretty rapidly. That's going to be about right here. And I'm willing to bet the next one probably goes off the graph. But we really can't tell what's going on next to the asymptotes. So we are going to have to pick some fractions that is right near the asymptote to see exactly what's going on. So let's continue with our t-chart. And on the right side, let's try to pick here, right side of the asymptote, let's pick 1.5 and 1.25. And on the left side of that asymptote, let's go with 0.5 and 0.75, and let's see what's happening closer to the asymptote. So when you replace the x with 1.5 in the equation, you're going to have 1.5 to the third power over 1.5 minus 1, and that's going to equal 3.375, and then we will divide that by 0.5, and we get 6.75. And then when we do that for the rest of the graph, this is the t-chart that is results. So when we graph those points, we got 1.5, 6.75, which is about right here. And 1.25, 7.8125, which actually is about close to 8. So you can see on this side right here, what's going on is that it is very rapidly dropping from the asymptote until it gets into this area somewhere. It may not be exactly that point, and then quickly turns and goes back the other direction. And then we have 0.5, negative 0.25, which will be about right here. And then 0.75, negative 1.68, which is about in this area. So what's going on this side of the graph is it comes in pretty steep, and then it kind of levels off in this area a little bit, and then drops very rapidly again. So you can see that when you have rational functions with exponents, you can get some very rapidly changing graphs and some unusually shaped graphs. Let's try another one. This is f of x equals x minus 3 over x plus 1. So again, the first thing we will do is try to find the asymptotes. There is a vertical asymptote at x equals -1 because that is what would make the denominator equal to 0. So I will graph that in there right now. And notice that the degree of the numerator and the denominator are both 1s. They're both x to the first powers. So that means we will look at the coefficients, and those are also both 1s. So the horizontal asymptote will be located at 1 over 1, which equals just 1, or y equals 1. So that will be right through here. I'll draw that in. And then we'll pick some points that is close to the vertical asymptote. So on the right side, that could be 0, 1, and 2. And on the left side, that could be -2, -3, and -4. So again, when we plug these into the original function, I would have 0 minus 3 over 0 plus 1. So when x equals 0, then that means y would equal -3. And then do that again for 1. So that would be 1 minus 3 over 1 plus 1. So that would be -2 over 2, which equals -1. And then the rest of the chart looks like this. And then when I graph those, so I graph 0, -3, which is going to be down here. 1, -1. 2, -1/3, it's about right here. And then -2, 5. -3, 3. And -4, 7/3 is about 2 1/3, approximately right here. Now this is going to look a lot more like the reciprocal functions because we have asymptotes going vertically and horizontally. We know that the graph is not going to change directions very rapidly because they are going to continue to approach the asymptote as they approach infinity. That's the definition of an asymptote. So that's why the graph is going to look like this. So a little bit easier than the last one we just did when there was just a vertical asymptote and no horizontal asymptote.